Let's talk a little bit about exponentials, logarithms, and how to differentiate them. This is section 5.3 in your lecture notes. Exponentials are really special functions with a lot of applications in the natural world, including physics. An exponential, very simply, is given by something e to the power of x, or more generally, something that looks like y0 e kx, or another form is simply e to the power of kx. One thing that really distinguishes exponential functions is that in its simplest case, where it's just e to the power of x, the derivative that we can write like this, or in Leibniz notation, d over dx of e to the power of x is the function itself. This means that the rate of change of an exponential at any point is the value of the exponential at that point. This is quite unique in physics. The other derivative that's very useful to know is when you have e to the power of kx, which is simply k e to the power of kx. We'll see that you can get this very simply if you use chain rule. More generally, if you're differentiating a function that's e to the power of some function of x, and we'll see this with chain rule as well, the derivative is the derivative of that function times the original. These are things that you should know already, but with chain rule, even if you don't know, you can very easily obtain them. But what about if we have a function that's a to the power of x? In this case, we can't really use the differentiation rules, but we can actually derive one. Let's make some space. This is our goal, to try to differentiate a to the power of x. And with the differentiation rules that we've seen so far, we can't really do it. It's easy enough if it's e to the power of x, but not necessarily if it's another base. How can we do this? This is therefore a great opportunity to show you how, by operating the expressions and making them look like something that you can differentiate, you can get the answer. This usually involves rewriting what you want to calculate in some form that's more familiar. For example, something like this. You can write this obviously as a is recovered if you get e to the power of ln a. This means that a to the power of x is the same as e ln a to the power of x. With the properties of logarithms, it means that this is also equal to e x ln a. If you realize this, then it means that we can write a to the power of x as e x ln a. Why is this good news? It means that we can differentiate both sides. Let's use Leibniz notation. And from this side, from what we know, the derivative is simply the derivative on the function on the top multiplied by e to the power of x ln a, which means ln of a e to the power of x ln a. This makes it very simple because this is our original a to the power of x. This is what we've looked at. We actually got it from here and using this simple property, which means that the derivative of a to the power of x in general for any base is given by ln of a and then the original function. You can obviously memorize this if you want, but you don't have to, and you can always re-express if you can write a to the power of x, something to do with exponential function, which you can differentiate. You can always obtain this. And this is a very good lesson of the kind of manipulations that you're expected to be doing in Physics 101, and that will really serve you throughout your degree.